All right, you guys can see that, right? Is that right?
Mm-hmm.
Okay, so today we're going to calculate optical selection rules and do scattering. And so here's the definition of what we did last time. The rate of optical absorption depends on the matrix element, the dipole matrix element squared, as you see here. And so we have to calculate the dipole matrix element. And so now we're going to calculate it, and we're going to see when it equals 0 and when it doesn't equal 0, and that's what an optical selection rule is. So we're going to calculate the dipole matrix element that connects to atomic states. So we're going to calculate when an atom can absorb a photon, basically. And so we have to calculate that dipole matrix element because that determines the absorption rate, which we calculated using that Fermi's golden rule trick last time. So let's calculate this dipole matrix element. So here's our atom on the right, and we have our initial state and our final state. And so let's calculate the dipole matrix element that connects the initial state to the final state. And so to do that, we got to put it into an integral. And so the integral is a spherical integral. And so we have a radial part. And so it's, then we have the angular part, sine theta, d theta, d phi, right? And so this is our, volume, d volume. And then we have our wave function, our final state wave function, which is going to be, we have a radial component, right? N prime, L prime of R. And we have the angular component, and it's complex conjugated because it's on the left. So that's theta phi. And then we have the operator in the middle, like usual. And then we have the final state on the right. The initial state on the right, R and L of R, Y, L, M of theta phi. Okay, so they were just plugging it in, and we're just calculating the matrix element. It's, you know, it's some tedious algebra because it's, you know, it's in spherical coordinates, but it's tedious, but it is somewhat straightforward. So now,
in the R sub NL arguments, is there a need to put the vector arrow over the R? Isn't that just a scalar R?
Oh yeah, good point. Yeah, that's right. So let's fix that. And then this also has the L prime, M prime. Okay, does that look good? And so now we're going to do a trick. So now we're going to do a math trick, which is somewhat tricky, but it's not hard, but it's the kind of thing you'd never think of on your own until someone shows it to you. Change this volume a little bit. Okay, so the math trick is that we're going to take this R that's there, and we're going to do a trick. We're going to rewrite it in a very tricky way. So let's first notice that what R is, it's just going to be X, X hat plus Y, Y hat plus Z, Z hat. Okay, so that's what R is. But then let's rewrite it in a funny way. Well, not a funny way. Let's just write it in spherical coordinates. In spherical coordinates. And let's just remind ourselves what spherical coordinates are. We all know, but let's just remind ourselves some of the details. We have our R. This is our X, Y, Z. This is theta. We drop ourselves down there. We have this thing coming out like that. This guy is going to be phi. And the length of this guy here, you guys remember what the length is of that vector? Anybody remember?
R sine theta.
Exactly. This guy's R and this guy's R sine theta. And so then we have our Y, which is R sine theta times what? Do you guys remember? R sine theta times
Something like d theta d phi, something like that.
No D's yet. We haven't done the D's. This is just pure trigonometry. It's the component. It's all in the plane. R sine theta times something. Do you guys remember? It involves phi.
For x, it's cosine phi.
And for y, but I didn't ask for x. I asked for y.
Oh, then that would be sine phi.
Exactly. Perfect. And then, of course, we can drop it down onto the x-axis, like you just said. We got this guy. And so that guy's going to be R sine theta cosine phi. Okay, so I know this is stuff that you guys all have seen before. But that means then that we can write the R as x, which is R sine theta cosine phi, x hat, plus y, which is R sine theta sine phi, y hat, plus z, which is something z hat. Guys, remember, what is it z hat? What is it times z hat? What's the z component?
R cosine theta.
Exactly. R cosine theta. Exactly. That's this guy. R cos theta. That guy. Yeah. Okay. Good. So you all remember that. Okay. So this is the R vector, the operator. So that's not. It's tedious, but it's not hard. But now comes the trick. The trick is that we can do this. And it's just a simple rearrangement. The trick is that I can rearrange this to look like this. R equals square root of 4 pi over 3 times R times z hat y10 of omega plus minus x hat plus I y hat over square root of 2 times y11 of omega plus x hat plus I y hat over square root of 2 y1 minus 1. Okay, and this is because y10 is proportional to cosine theta. You can just look these up in a book, and y11 is proportional to sine theta e to the I phi, and y1 minus 1 is proportional to sine theta e to the minus I phi. And you can just look those up in the book. You've all seen this before, you know, last semester, although you might not remember it, but it's just the definition of spherical harmonics. And when I use this notation, omega, I mean for omega to refer to the angular coordinates. It's just a notation that I like to use, so as not to be too confusing, because it's sort of referring to solid angle, which will be important later. Okay, so so that's just a definition, and so I'm not going to derive that, but you can derive it. Just plug it in and just work through the algebra, and you can just see that it's true. It's just some tedious algebra. But then what we're going to do is we're going to plug. So the trick for deriving selection rules is to plug this in into the dipole matrix formula. The NLM R and Lm. So plug that into our integral. And so when we do that, then this is what we get. And it's big and ugly, but it's simple. It's simple but tedious. You know, one of those common things that happens so often. But before I plug it in, let's just notice something. Notice that I can, and this is sort of the thing that's like not obvious, but if I take the vector r, the operator r, which is a function, then with that function, the function, or it's like the function slash operator r has associated with it angular momentum. And that's kind of the insight that is like not totally obvious until someone writes it out for you. And there's some angular momentum associated with that. And what is it? I'm asking you a question. What angular momentum is associated with the operator r? Tell me. It's a question. Look at that formula and tell me, what is the angular momentum associated with the operator r?
Is it 1?
Yes, and that's correct, because look, if I have a function YLM of theta phi, this function is the eigenstate of an operator. Do you guys remember what operator it's an eigenstate of, the spherical harmonic? Do you guys remember? It's an eigenstate of some operator.
Is it big L squared?
That's exactly right. That's exactly right. And so when I look at this function, YLM, in my mind, I'm thinking, oh, that function has angular momentum. That function represents angular momentum of L. And the reason why I say that is because a particle that has angular momentum L, its wave function is represented by that function. That function represents the wave function of a particle with a well-defined angular momentum. Okay, so this function has angular momentum of L, okay? Angular momentum. So when I look at the function R, and I see that it's constructed of these YLMs, and they all have L equals 1. It's like, oh my God, that function has angular momentum 1, all right? So the operator R is representing a function, a wave function that has angular momentum of 1. And the Z component is not so well defined. It has some Z component of 0, some Z component of 1, and some Z component of -1. So the Z component is not so well defined. It has a little bit of each of the 3 possible ones, but the total angular momentum is very well defined. So that's the insight. And what that means then is that, look, this guy has angular momentum L prime. This guy has angular momentum L. And this guy has angular momentum L equals 1. And so all the components in this integral have well-defined angular momentum. And that is what we call symmetry. That means that there's symmetry, because if something has a well-defined angular momentum, then we say that that object is symmetric. It has sort of, that means that the angular momentum tells us how it behaves under rotation. It has a well-defined angular momentum, so that means if I rotate it, that rotation sort of has a, it changes the function in a well-defined way. And so that means that all of these components have rotational symmetry, a certain kind of rotational symmetry. And so that's why we say that symmetry plays a role here. And I'm not going to go, you know, symmetry is like a big topic in physics. And so I suggest that you all try to learn as much as you can about it, you know, on your own or in classes, whatever. But I'm just mentioning that this is a time and a moment in physics where symmetry is playing a role. And symmetry is playing a role in this problem because all the pieces that go into this matrix element are symmetric under rotation. They all have well-defined angle momentum. So that's sort of underlying this whole process. So, and that's the language that people use, but often people use that language, but it's sort of mysterious. You know, if they say, hey, it's symmetry, and you're like, well, what the hell are you talking about? I know that as a student, I always was confused about symmetry, and I still do get confused about it. I'm not like a master of symmetry, but I've been around long enough to know that it's important, and so I'm trying to express that to you. So this is a time and a moment when symmetry is very important. Okay, so let's plug that into our integral, and when we do, this is what we get. We get this. We see that our dipole matrix element, which connects the initial and final states, is equal to, so I'm going to write it all out. I just plug that in, just doing some, you know, maybe skipping a line or two of algebra, but it's no big deal. 4 pi over root 3. And now I'm going to separate the radial integral and the angular integral. And so the radial integral will be this, r cubed dr. And that's going to be r complex conjugate n prime l prime of r times r and l of r. That's the initial and final states. And so that's the radial part. And now that's going to multiply the angular part. And so now for the other part, it's, you know, it's kind of a big mess, but I'm going to sort of piece it out. That this is going to be multiplying this z hat times now d omega. When I say d omega, that's sort of shorthand for sine theta d theta d phi, which is solid angle, a little bit of solid angle. So that's shorthand. And we'll talk more about solid angle soon. Maybe this is a good time to talk about solid angle. What the heck? Let's just talk about solid angle for a moment. Here's angle. You guys know that angle is like this. Like if I have an angle, this is dl, and if this is d theta, that angle, and if that's r, then you guys know that dl, what's dl in terms of r and d theta? Somebody tell me. Where dl is that little arc length.
DL
What is
r d theta.
Exactly. And in some sense, that's the definition of angle. That right there, that geometric construct is the definition of angle, because then I would say that d theta is equal to dl over r. So that construct is the definition of angle. That's what angle is. It's the arc length divided by the radius. So that's the angle that you're all used to. But then that's in 2D. But then what we do for solid angle, we generalize it and we call it solid angle. And it's just a generalization of your old friend. And let's just generalize it. Let's see if I can do this without screwing up. X, Y, Z, R. Let's see, here's theta, R. Okay, so then what we do is, and here I have phi. And so what we do is we say we have, damn it, keeps doing that. And this is R, and so we can define a little area here on the surface of the sphere, and that area is it's going to be R squared sine theta d theta d phi. Do you guys, so that's the area, the little bit of area, dA on the sphere. And that's just by doing the geometry of looking at the, if I move it if I move that R vector a little bit in theta and a little bit in phi, it traces out an area. dA on the sphere, dA equals R squared sine theta d theta d phi. And so then I can, and you guys know that because that comes from the fact that the volume, the little bit of volume is going to be the little bit of area times dr, which is going to be equal to your old friend R squared dr times sine theta d theta d phi. Did I get that right? Yeah. Does that look right, guys? Look familiar? And so what we do then is we say that if dA equals that, then we can say that what does dA over R squared equal? And dA over R squared is equal to sine theta d theta d phi. And this is the definition of solid angle. And I want you to see how it's exactly the same as the definition of regular angle above it. Because notice how an angle is a dimensionless quantity. See, notice how it's up here, it's dimensionless, no dimension. Because it's a length over length. Whereas here, I've now generalized this into 3 dimensions. You see how there's no dimensions to it. It's solid angle, but it's just dA over R squared. And if I integrate it over a sphere, then a sphere has area 4 pi R squared, right? So what's the total solid angle over a sphere? Well, first for a circle, I have a circle has the circumference. The total circumference of a circle is 2 pi r. And so the total angle of a circle is the total circumference 2 pi r divided by r equals, what's the total angle of a circle?
2 pi.
Exactly. And now let's do the same thing for solid angle. A sphere has area 4 pi r squared. So the total solid angle is going to be 4 pi r squared divided by what? By definition of solid angle? What do I do? Yeah.
R squared.
Exactly. Because it's area divided by r squared. So the total solid angle of a sphere is 4 pi r squared over r squared equals 4 pi. So the total solid angle of a sphere is 4 pi in analogy to the total angle of a circle is 2 pi. Now, I don't know if you guys, so how many of you have seen this before? Just say yes. Just shout it out. I'm just curious. Yeah. How many, what?
Yeah.
Anybody else?
Yeah.
Okay, that's at least 2 people. All right, well, good. So, because I know these are, you know, because I remember when I was an undergrad, I don't think anyone ever showed me this, because like there are certain little things that just slip between the cracks, you know, in different classes. And I noticed that some people never learn solid angle, you know, but solid angle turns out to be really important. So, and it's really important for our discussion of scattering. And that's why I'm just mentioning it here. Okay, so let's keep going. So that's definition of solid angle. Let me say solid angle. Just a little primer on solid angle. Okay, so that's why I'm using this d omega here, because that's just shorthand for sine theta d phi, because that's just a differential solid angle. Okay, so then we have y star L prime M prime of omega, and omega just means, you know, theta and phi, because I'm just sort of using like solid angle definitions now. Y10 omega YLM omega plus, and then we have the other part. Sorry, it's a big ugly integral, but it's a very important result, so it's worth going through the details. Plus I y hat over square root of 2 times, now there's an angular integral here, which is d omega y star L M L prime M prime of omega y11 of omega YLM of omega plus, and then x plus IY square root of 2 integral over d omega y star. This is a messy little expression, but I don't know a more elegant way to do this derivation. I looked in various books and I could never find an elegant way to do this better than this way. In fact, I think this is the best way, my way. Okay, so that's the expression then for the dipole matrix element connecting the initial and final states for an optical transition in an atom. It's that. And I just want you to see, like, the thing that you see, this is like, you know, when you look at this thing, it's like, remember, this is like the final state. This part comes from the R operator, and this part comes from the initial state. So I just want you to remember what we got here. But this is an expression that sort of shows you the full symmetry of the expression. You can sort of see all the angular momentum components in, you know, all together. Now, normally you would look at this, and what I would like to say is, you know, normally if I had this, check it out, if I had this d omega YLM theta, mixing my notation. If I had this, then we'd be very happy, because I would just say that, because if I have this kind of an integral, then I say that's equal to what? Somebody tell me. Somebody tell me, what's that equal to?
Would that be two Kronecker deltas? So like delta L prime L and delta M prime M?
That's exactly right. Because the YLMs are orthogonal. That's exactly right. So if my integral looked like that, we'd be very happy, but it doesn't, because it doesn't look like that, because instead of having just 2, I have 3. So the orthogonality is not like totally obvious, you know, when you look at the integral that we have. So it's a little more complicated. So what we're going to do is we're going to do something that's called the addition theorem. And it's a real thing, use the addition theorem. And the addition theorem is basically just, it just comes from the addition of angular momentum. And the addition of angular momentum, to do the addition of angular momentum, you remember that, you know, if we adding angular momentum, which is a change of basis. Then we have L1. Then we have, if we're adding L1 plus L2, then we know that we have the total angular momentum can be L1 plus L2 to L1 plus L2 minus 1, all the way down to what? What's the lowest possible total angular momentum?
The absolute value of L1 minus L2.
That's exactly right. So those are all the different values of total angular momentum that you can have. And so what that means then is that if I have, and if I try to write the total angular momentum state, eigenstate, then that's going to be equal to a sum over the all of the product state, right? Of L1, M1, L2, M2. Okay, so that's what it means to add, and we've gone over this, but it's a restricted sum, it's constrained, and the constraint is that M1 plus M2 has to equal what? Can you look at that formula and tell me what it has to equal?
Is it L total?
No, because we're talking, because the M's refer to the Z component, but that's close. What else could it be?
M total.
Exactly. That's exactly right. So it's a constrained sum. And then you have these constants here in front. And the constants, it's a sum over M1 and M2. So I'll just write the constant like that, the Klebsch-Gordon coefficient. Okay, so that is something you know. We've done that, and that looks familiar to you. But then now we're gonna do the new thing. We're gonna invert this relationship. And intuitively, you know that you can do that. Because if I can go one way, then why can't I go the other way? Okay, let's go the other way. So now let's invert this relationship by writing L1, M1, L2, M2 is equal to, now it's going to be a sum over L total. And it's going to be a sum over all the different L totals and M totals. And this, so this is, we're going to be summing over all the different L totals. Okay, so that's an inversion. And there's going to be a constraint where M total is equal to M1 plus M2. Okay, so this is the addition theorem, this relationship. That's the addition theorem. And I just want you to look at it and realize that it's a sort of a, Jesus Christ, it's sort of a simple thing, or an intuitive thing. Okay, that's the addition theorem, and it's like an intuitive relationship. Okay, so it just means then that it's just an inversion of the addition of total angular momentum. So if I can write, if the total angular momentum is equal to a sum over all the product states, then a product state is equal to a sum over all the total angular momentum states. So it's just an inversion. So that should seem sort of intuitive to you. And so now what we have is, the reason why I do that is because, look, we have these things. These are product states, because this thing is like 1, 0, L, M. And that's a product state. You see what I'm saying? That's, and this one is like the state 1, 1 hitting the state L, M. And this guy is like the state 1 minus 1 hitting the guy LM. And so you see these are, so we have these product states. So what I'm going to do is we notice that we have these different product states. And so we notice that what we have, I'm going to use it because I'm going to notice that I have, we have 1 M prime, right? Because that's these different M's, you know, the M prime, the 0, 1, and minus 1 is going to hitting, I'm going to use this. We know that this is going to be equal to some coefficient C L plus 1, which is going to be L plus 1, and then I have to add the M total is M prime plus M plus some coefficient of L M prime plus M, and some coefficient of L minus 1 M prime plus M. Okay, so I'm using this. This is just the addition theorem. So that means if I have this product state, I can write it in terms of total angular momentum states. Because if I have the 1 and if I have the L, then there's 3 different total angular momentums I can have. And so that's where I get the L plus 1, the L, and the L minus 1. Okay, so it's sort of like, it's like 1 plus L is equal to L plus 1, L, and L minus 1, okay? And so that means then that using this kind of language, I see that I have y10, if I have the product of the function y10 and ylm, then that is equal to some, that is going to be, I'm going to sort of not do all the correct coefficients, but it's going to be equal to some constant times y L plus 1 M plus some constant y L M plus some constant y L minus 1 M. And if I have the product y11 y L M, and these products are coming from here, you see, that's where I want you to see, you know, that I'm, it's these products, you know, that I'm talking about, these products. I'm rewriting them in this clever way. Then that's going to be equal to D times Y L plus 1 M plus 1 plus F Y L M plus 1 plus G Y L minus 1 M plus 1. And then I'm going to have the third one, which is Y1 minus 1, the product YLM is equal to H Y L plus 1 M minus 1 plus J Y L Y, M minus 1 plus K times Y L minus 1 M minus 1. Okay, now there's a reason why I did this, because see these things, because now we can plug into that integral, plug into integral. And that means if I plug these into the integral up there, that means it really simplifies, because now I can get rid of these products, and then I go in and I get just this simple pair of spherical harmonics. So if I plug them in, then you can see that now I get the cancellation, because now I get the orthogonality cancellation. Orthogonality cancellation. And the orthogonality cancellation means that now these integrals are all going to cancel. So everything so now you can see that everything cancels except for when those coefficients are equal, and when the coefficients can only be equal when I need L prime, and so now this is the final state. L prime has to equal L plus 1 or L or L minus 1, while at the same time I need M prime can equal M plus 1 or M or M minus 1. So because when we plug these guys back into the integral, we see that everything cancels unless this is true. And so what that means then is that L prime minus L has to equal plus 1 or 0 or minus 1. And M prime, the final state minus the initial state M, has to equal plus 1 or 0 or minus 1. And so that's the case. So the integral equals 0 unless this is true. But then there's another thing, but then we notice you can, there's another thing that you can notice. It's easy to show that if L prime minus L is equal to 0, then we can show that the integral equals 0. And that's a homework problem. That's problem number 9.13. So you can show that if the final, basically if the final state angular momentum equals the initial state angular momentum, then the integral does equal to 0. And so this is actually, this one also equals 0. And so, so then what we say, so the final selection rule is this. We say that the dipole matrix element between initial and final states equals 0 for atomic transitions, for optical atomic transitions, unless the change in angular momentum between the states, between the initial and final state, is equal to plus 1 or minus 1, and the change in the M value, M, is equal to plus 1, 0, or minus 1. So it's so the selection rule is actually very simple and easy to write, but deriving it is quite tedious. I mean, we just derived it. I'm sorry it took so long. I've actually looked for a simpler derivation. I could never find one. And so now let's use it. So suppose that we have this state. Suppose that we have an atom. That's how I'd like to draw atoms. And it's, it's sitting in some state and we're shining light. And suppose that the atom is in this state. Let's suppose that it's in this state. It's here. And it's in the state 3, 2, 2. That's NLM. And then I want to know, can it absorb light and go into the state 4, 2, 2? No, 4, oops. 4, 3, 2. So is this allowed? Okay, I'm asking you a question. Is it allowed? Tell me. Well,
Yes,
here,
it
let's.
is.
Okay, well, let's work it out. I mean, so delta L is equal to what? Tell me, what's delta L?
1.
And what's delta M?
0.
Yes, good. And so it is allowed. That's good. Yes. So that can happen. But now let's do a different one. Let's do this one. Now let's do a different one. Here's my atom, and here's a bunch of states. And I have the electron sitting in this state. It's in the 3, 2, 2 state. And I want to know, can it go up to the 4, 1, 0 state? Is this allowed? Well, let's calculate it. Delta L equals what? Tell me. Delta L equals what?
-1.
Is that okay?
Yep.
Good. And what about delta M?
-2.
Is that okay?
Mm-mm.
That's right. So that means that that transition cannot happen. When I shine light on an atom, it will not go from here to there. All right, that's what a selection rule means. And there's a really famous one because, I mean, check it out. It's like, suppose I'm in this state, 2, 0, 0. So then the question is, if I shine light on it, can I cause it? Because remember, the transitions go either way. You can have stimulated absorption, but also stimulated emission. So the question is, will this guy fall down by emission of a photon into the ground state, which is 1, 0, 0? So is this allowed? Let's figure it out. So delta L equals what? Delta L
0.
equals what? What?
0. 0.
And delta M equals what?
0.
Is that allowed?
No.
That's right. So that means that state has a very long lifetime. It doesn't fall down very easily. It's hard to get that guy to fall down because he doesn't want to emit a photon. And there's one last thing to notice is that notice that these transitions, the transitions have delta L equals +1 or -1. That means that when I absorb a photon or emit a photon, my angular momentum is changing by how much? My angular momentum is changing by how much? Say it.
It's not changing.
Delta L. When I emit.
+1 or -1.
So my angular momentum is changing by how much? Well, you just said it, +1 or -1, but it's changing by 1. It's either, going up or down. It's changing by 1. And what are the units of angular momentum, by the way? By 1 what? Like, what is a unit of angular momentum?
Isn't it h bar?
Yes, that's exactly right. It's h bar. It is h bar. Okay. So that means that, my angular momentum is changing by h bar, which we just say 1, L equals 1 refers to 1 h bar. So now I'm going to ask you a question. What is the spin of a photon? Spin is another word for angular momentum. So now I'm asking you a question. Does a photon have angular momentum? And if so, how much? That's my question to you. How much?
It has a spin of 1.
That's right. Photons have spin of 1. Now, in our theory, in our undergraduate quantum mechanics of this course, we don't really have photons. We have not quantized the electric field, the electromagnetic field. To do that, you need to take field theory, quantum electrodynamics. So that's beyond this class. But even without quantizing the electromagnetic field, I think it's very beautiful that just using these very simple time-dependent perturbation theory ideas of this undergraduate course, you can just see how the photon has spin 1. It's sort of, it's like the quantum mechanics does not fit together. You know, for the quantum mechanics to work and fit together, you need to have the photon have spin 1. But that's something that, you know, to actually derive that, you got to, you know, do more fancy field theory, blah, 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 quantum electrodynamics and all that. But even without doing that fancy stuff, you can see, even from this very simple theory, that there is an angular momentum associated with the photon. And so I think that's quite beautiful, you know, to notice that. Okay, enough of that. Wow, that took a long time. Okay, so let's move on to the next topic, okay, guys? But at least, you know, at least we did that in some depth. So I feel kind of good, like you guys, you know, that was a, you know, we actually did that topic in pretty good depth. So the next topic is scattering. And so let's talk about scattering. Okay, so now this is a big change, you know, so reorient your mind. This is the next big, this is sort of the last big topic, or not the last, but yeah, but almost the last big topic. One of the last, this is almost the last big, well, I'd say this is the last big topic of this course. I mean, we still will talk about WKB, but that's like a little topic. But this scattering is a big topic. So let's talk about scattering. So scattering is this. I mean, scattering is when you bounce something off of something. Boom, here's a wave, and it bounces off of this thing, and it goes into a new direction, okay? It used to be going straight, but now it got scattered into some angle theta. That's scattering, okay, in a nutshell. But what does it mean more generally? You know, when people talk about scattering, it's a very big, this is a very big topic, because here's the thing. In quantum mechanics, and if you think back, most of the quantum mechanics you did, at least last semester, and even this semester too, we're always talking about bound states. You know, I always like to say, hey, you know, I have some box and I have these quantized states in the box. The box could either be a Coulomb potential, a simple harmonic oscillator. It could be a soft wall, you know, a finite potential. You know, there's all these different types of boxes. And then you got these quantized levels in the box. But once you get out of the box, the levels become continuous. You see that? So here, the levels are quantized. But when you're free, the levels are continuous. And so when we talk about scattering, we're talking about the continuum states. This is scattering. Scattering lives here in the continuum. So at one level, scattering just means bouncing something off of something else. Okay, it's very simple. But at a deeper level, when we talk about scattering, scattering is the quantum mechanical theory of continuum states. So it's a very deep and very big and very important topic. All right, it's the theory of continuum states. Why do continuum states matter? Why? Why do we care about them? Well, we care about them a lot because for an object to move, that means the object is, you know, this is position. For an object to move, it starts here, and then at some time later, it moves here. That's what it means to move. For something to move, it means its wave function, like the center of mass of the wave function, moves. That's what it means for anything to move, like my finger is moving, you know, my head is moving. Anything that moves, that means that the wave function that describes those particles is literally moving in space. Now, to move, then you cannot move, and this is a big important point, for something to move, you need to have continuum states. You need to have these, and if you really want to like move, you know, over, you know, like free particle to move in space, like an airplane is moving, then you need the continuum states. You know, you need to have these continuum states. That's how particles move. And so, so another way, so when we talk about scattering, scattering is the theory of things that move. And I guess when I say things that move, like, I mean, in principle, I could have like a molecule that's vibrating, and you might say, oh, it's moving. Look, the atoms are vibrating. Okay, well, that's true. The atom is bound and it's vibrating. But when I say move, what I really mean is to start at one location and go somewhere else. Okay, that's what I mean when I say move. I mean to like the way you get in your car and you drive, you know, to the store. You're moving from your home to your store. You're moving somewhere. You're not just oscillating, you know. And so so scattering is the theory of things that move. So in quantum mechanics, you can't move without continuum states. You need the continuum states to get places, you know, like when you shoot an electron at something, or a photon, you know, when you have your flashlight and the light goes out of your flashlight, those photons are moving. And so that means those photons are utilizing continuum states. The photons are occupying continuum states in order to get from your flashlight to the wall. They have to occupy continuum states. That's scattering. So I just want you to see that's a big, big topic. It's very deep, very big, very important, because it's very important to us to move, right? You know, things, it's, you know, we need to move. Okay, so let's talk about things that move. So you've already done it. You already did scattering, already did it in 1D. You've done it. You did this theory of scattering. You didn't even know it, but you did do it. This is the theory of scattering in 1D. I'll remind you what it is, because, you know, when you did it, the professor did not call it scattering. I don't know what they called it, but they didn't call it scattering. This is the theory of scattering in 1D. I have a potential, and I have some energy, and this is V, and I have a wave function that's going here. And that's my particle, e to the I kx, and it has some probability to reflect. And that wave function is e to the minus I kx, and then it has some probability to transmit. And that's e to the I kx. Ha, this looks familiar, right? Somebody says I have a particle with some energy, and I'm hitting this finite potential, and so I have some probability to reflect and some probability to go through. That is scattering. Okay, so this is the theory of scattering. And so on this side, we say that the wave function on the left is equal to, I have my incident e to the I kx plus my reflected e to the minus I kx. Because on the left-hand side of the potential, I have my amplitude. My particle might be going forward, but it might be going backwards. I have some probability to go forward, but also a probability to go backwards. So that needs to be reflected in my wave function. It has to have both components. But on the right-hand side, my wave function is t, e to the I kx. Yeah, you guys remember that? And the probability to reflect, you guys remember that from last semester, equals what? Tell me, from what you see that I've written down. What is it? Probability to reflect. I'll give you a hint. It involves this part. That's the part that reflects, R times e to the minus I kx. And what is the probability to reflect?
The R?
That's right, but it's not just R. What do you got to do to it?
R squared, quantity squared.
Exactly. Because remember, to get a probability, you always are taking the wave function and squaring it. So that's how to remember it. You know, you got to square it to get a probability. And what's the probability to transmit? What is it? Tell me.
Quantity t squared.
Exactly. So you did it. And how did you get R and T? Well, actually, I won't force you to, like, you know, remember all the details, but I want you to think for a moment. How did you get R and T? Well, what you did to get R and T, you did the boundary conditions. Remember, you matched the wave function at the boundaries, and you had the, you know, you had the exponential dying in here and growing, and you matched them. Remember, you did all that. Okay, so it was a lot of work, actually. And that was the theory of scattering in 1D. You did it. And so I want to, but you didn't use the language of scattering at the time. So now I want to introduce the language of scattering, like, you know, because we're going to do, the thing is, okay, let me just make a point, which is that normally in this class, you know how all the time I say, okay, let's do the problem in 1D, and then to generalize into 3D, it's very trivial. We just, you know, it's just adding a few dimensions. It's no big deal. You know, I say that all the time. Oh, let's just do it in 1D. The generalization into 3D is trivial. And that I say that because it's usually true. But it turns out that for the theory of scattering, it's not true. Scattering is one topic where the one-dimensional theory is very simple, but the three-dimensional theory is actually much more difficult. And so the generalization from 1D to 3D is actually very non-trivial for scattering, okay? So that's why I want to sort of work up but the 1D case is the one that you understand. You know, in the 3D case, you don't understand, because, you know, that's why you're taking this course. That's why I'm teaching it. But okay, so let's try to use the theory, the language of scattering in 1D, and then we will go to the 3D case. But I want you to see the concepts in 1D, and then because then we're going to utilize the same concepts in 3D. So the thing is that in 1D, you don't actually need the concepts that much. In 3D, you absolutely need them. But that's why you guys didn't do them, because in 1D, it's not so important. But let's do it. So the first important concept is probability flux. Now, you guys learned this in 1D, and you probably were wondering to yourself, why the hell am I learning this? It's just some weird formula that you derived, and you probably never use it for anything useful. And that's because there's not much, you know, to do with it in 1D. But it turns out that probability flux is a very important concept, much more important than you were taught, much more important than you think. So here's the little formula for probability flux that you all learned and probably don't even remember. It's this one, psi star d psi dx minus psi d psi star dx. Okay, so that's probability flux. You guys all learned that. Do you remember it? Remember it? Somebody tell me, what's the units of probability flux? Just the units. I'm not even asking you to remember the formula, I'm just asking you to remember the units. Does anybody remember even the units? The name should tell you the units, probability flux. Whenever someone says flux, they mean per time, right? So what's the units of probability flux?
Per second.
Yeah, good. It's probability per time. And in 3D, a flux has units. I just want to say probability per area per time. Okay, and so this concept of probability flux is very generalizable from 1D into 3D. So I want you to think of that. So the probability flux, when you think of flux probability, the probability is flowing like water. So this is how I want you to think of it. Probability equals water. So now I want you to really think probability is stuff. You know, it's conserved because, you know, if there's a finite amount of probability, the total probability is always 1, right? It's conserved. Probability is conserved. Probability is like water, it's stuff. So for scattering, it's very important for you to think of probability as stuff. And now the analogy is not just words, like, you know, like a sort of, you know, analogy. There's actually a perfect mathematical mapping, okay? All right, because now we're talking about probability flux. So if there's a flux of probability, that means probability is literally stuff. It flows. It's not, I'm not saying that, it's not like it sort of flows or it seems to flow. It literally does flow. Probability does flow. And the formula for it is right here. I wrote it down, J. It's that probability flux. So probability flows, it's like water. And so if I look at that scattering problem above, so in that, for the 1D scattering above, then I could calculate the probability flux on the left side just by plugging into that formula, you know, psi star del d psi dx minus psi d psi star x. And if I calculate it using this wave function on the left, then I'm going to get a probability flux of h bar k over m times 1 minus r squared. And on the right, I'm going to get a probability flux. If you just plug it into the formula, you're going to get h bar k. And I suggest you all go do it, of t squared. Okay, just plug it in. Now here's the thing. If the probability is flowing on the left and it's flowing on the right, and probability is conserved, I don't create it or destroy it, then what is the relationship between the probability flux on the left and the probability flux on the right? What is the relationship between them? Somebody tell me.
They add up to 1.
What?
They add up to 1.
Well, total probability adds up to 1, but this is probability flux. So probability flux doesn't add up to anything because it could be going slow or it could be going fast. There's no, you know, it doesn't, probability adds up to 1, but what I'm talking about, I'm talking about probability flux. So think of water through a hose.
Oh, they're equal to each other?
Yes. Because if I take a hose and I define the right side of the hose and the left side of the hose, and there's water flowing through it, then the flow on the right has to equal the flow on the left, right? Otherwise, the hose will explode. Think about it. Hose will explode if the flows don't equal, because that means that the water is building up and it will explode. So I need that the flow on the left equals the flow on the right. Otherwise, probability is not conserved. Otherwise, it starts being created or destroyed. And so if you add those two guys up, then you'll notice that you have, so take these two formulas and add them up, h bar k over m 1 minus r squared equals h bar k over m t squared. And you'll notice that you get this very nice little formula, which leads to 1 is equal to r squared plus t squared. And that's a formula that you guys know from the past. That's just saying that this is your probability, total probability is 1. Okay, so because the probability to reflect plus the probability to transmit is 1. But now I just want to, okay, so we're just about to finish, but I just want you to, I want to recast this thought of probability in a different way. Let's think of the probability now. Let's think of it like in terms of flowing, in terms of probability flux. Think of it like this. If the way I want you to think of it now is, let's consider a barrier and I'm shooting a particle at the barrier. Think of it like this. I have this much probability going toward the barrier. But then when that so those arrows represent like water, like 3 units of water flowing. But when I hit that barrier, 1 unit of water gets through, but 2 units get bounced back, okay? So so this is incident and this is reflected, and this is transmitted. And that's the flux. Think of it in terms of flux. And so now if I say the probability to reflect, think about it for a second. The probability to reflect is going to be, well, how much reflects? It's this much, right? And how much was incident? It was this much was incident. And so the probability to reflect is going to be, it's going to be this. It's going to be the incident flux minus the transmitted flux divided by the incident flux. And the probability to transmit is going to be equal to this much divided by this much. It's going to be the J transmitted divided by the J incident. So this is a different way to think about probabilities in terms of flux, all right? And so if you actually calculate these quantities and plug them into this little formula that I just wrote, using this, by calculating these J's, and you'll see that the probability to reflect is going to be R squared, and the probability to transmit is T squared. You'll get the same formulas using your, J goes as, psi star, d psi, dx minus psi, d psi star, dx for those, for these quantities. Okay, so this is a good time to stop, but what I'm doing is I'm taking a problem that you've seen already in a different way, and I'm recasting it in a new way. I want you to think about, I want you on your own to look at the one-dimensional problem and to think of it in terms of probability flux. And I want you to think of the probabilities in terms of flux. And this is how you think of them. Okay, and so that's a useful exercise, and it will help you to understand the three-dimensional case, which is coming like a train. You can see it in the distance. The headlight is getting bigger and bigger, and it's coming right at you. Three-dimensional scattering is coming at you. Okay, bye-bye.